My name is Jeremy Jarrett, and I'm with Michael Idell from Kinetic Vision's Modeling and Simulation Group. Kinetic Vision is an Nvidia service delivery partner in the DGX compute specialty. I'm going to turn it over to Mike here to talk a little bit about the Coanda effect.
All right. Just going to start out here with a little bit of the history of the Coanda effect and Henri Coanda. So Henri Coanda was a Romanian inventor who worked in aeronautics over 100 years ago. He really started out and his main field of work was developing experimental aircraft early in the days of aviation. He detailed out the Coanda effect and was actually issued a patent by the French government in 1934. So per DJ Tritton in his book Physical Fluid Dynamics, the Coanda effect is described as the tendency for flows to attach to walls or to one another. So on the bottom right you can see two different images of multi-element airfoils. And the flap that's shown in the very bottom right image actually shows a jet of air flowing around the flap, which induces a pressure gradient normal to the flap itself and helps maintain attached flow. This is important especially for aircraft because that attached flow can help maintain proper performance from a lift coefficient standpoint of the actual full multi-element system.
The Coanda effect in reality is used in a lot of different industrial applications. So many you may almost not recognize it, but it's pretty ubiquitous. It's used in material handling, intralogistics, manufacturing, and commonly used in an implementation called an air knife, which can be used for drying, dust management, material processing, and things like pneumatic sorting.
Researchers have investigated Coanda nozzles as one way to help direct the flow downward towards the bottom of the steel strip and also maintain stability of the actual nitrogen jet so that you mitigate both the edge over coating as well as the checkerboarding pattern noticed. And this is really the application. It kind of forms the motivation for the nozzle that we're going to be taking a look at on subsequent slides. One of the important things that you need to think about when you're first setting up a SimNet case is how to non-dimensionalize the domain so that you don't wind up with any disparities in weight values. You want most of the weights to actually be between 0 and 1. One way to achieve this is by using a Reynolds number scaling to a fairly normalized domain. Here we took the same approach that's detailed out in many of the SimNet examples, and we in the non-dimensional domain we set density, the U velocity, and D values to 1 and solve for an effective viscosity to match the Reynolds number of a full-scale problem for an industrial problem of interest. The point cloud density is also something that's subject to user input. The sampling or the batch sampling of your physical domain is up to your specification. So the way that it was approached here for this 2D nozzle is that we started out with a background, which is shown on the bottom, the top right image, and then we also added in a high resolution region within what would be called the nozzle's potential core, where you experience a lot of velocity gradients. So to start off, we selected a baseline simple 2D case with no parameterized geometry as our beginning point for this Coanda jet exploration. It looked very qualitatively correct from the standpoint of the jet theory presented in the previous slides. There was slow convergence noted for this case throughout the training, and one of the culprits of this potentially is the fact that there was a sharp geometric discontinuity at each trailing edge of the nozzle. It was thought that potentially adding a radius of these to the edges of the nozzle could help speed up convergence, and in fact it did, and it was a factor of approximately 3. So qualitatively we did a comparison, and quantitatively we also made a comparison between the commercial code Fluent. So in the bottom left, the velocity contours generated by the Fluent solution that was set up identically from a geometry and also a physics standpoint as a SimNet, shown at the bottom right, they look very similar. One thing to note is that the velocity contours in the SimNet trained neural network did exhibit some non-zero velocities on the outboard sections of the jet. So from a quantitative standpoint, we compared the Fluent and the SimNet results at two different stations downstream of the nozzle exit. A couple of things to note. Peak velocities in the actual Fluent jet are slightly higher, whereas the outboard velocities are 0 for Fluent and non-zero for SimNet. So overall, a pretty good prediction, I'd say, by the physics-informed neural network that we trained with SimNet. Some discrepancies that we think that we can improve upon in the future.
All right, I'm going to talk a little bit about how we took these results and integrated them back into CAD with SolidWorks. If we looked at how we defined the parametric geometry for SimNet, you can see that we added a radius to both trailing edges, and then we took advantage of one of the trailing edges to change that radius as part of our parametric study. And you can see in the lower right-hand corner, by increasing that radius, you change the pressure gradient at that exit, and that's one of the parts of the Coanda effect that we're going to be taking advantage of in this design. As the radius gets larger, it will begin to look more like a flat plate. As the radius is smaller, it will produce exponentially increasing normal pressure gradient. And then you also have to take into account that as that radius changes, the surface area over which the pressure gradient occurs is going to have an influence on the jet angle. So if we look at our results out of SimNet and retrieve them over the design space of the changing radius, you can see indeed, as we look at the velocity contours, that jet angle changes as you increase the radius, and it is a nonlinear relationship. So now that we have some results coming out of SimNet, it's time to look at how do we integrate SimNet with SolidWorks. So this just shows the flow that we designed for interacting with SimNet. We start off in SolidWorks, and the user is going to specify this trailing edge radius. We pass that value through Python into an interface with SimNet. Python's going to retrieve the data from the neural network and the results for that specified radius in the parametric run. And then we actually do some post-processing in Python also to take a look at the velocity profiles and calculate an average jet angle, and then relay that jet angle back into SolidWorks. So this is the design for the air knife that we chose. On the right-hand side, you can see a normal commercially available air knife, and then on the left, we designed an air knife that takes advantage of this Coanda effect on the bottom surface. And as you interact with the CAD model, really what you do is just like using SolidWorks on an everyday basis. You're going to select your sketch. You're going to change the radius value of that lower trailing edge, and then that's going to adjust the solid model. And on the right-hand side, what you can see is we're showing the results at each different radius as we cycle through that design space. So here we've got the assembly. We're going to move into the component where the trailing edge is defined, and then we're going to adjust that radius. We'll turn on the jet angle body here so that we can see the jet. And then as you watch, we go up and click on our button that fires off the SolidWorks macro. And then you saw that jet angle change. Now we're going to move into a side view here and do this again. And if you watch that jet angle carefully, as we switch to a new radius, and then we push that SolidWorks automation, we go out and retrieve the information, we bring it back and adjust the jet angle, and you can see that really within just a couple seconds we get a result back, allowing the designer to really understand what direction that jet is as it's coming out of the nozzle. So we were really pleased with these results, and it was really a success, based on what we first set out to do. A few of the things that we want to do is we want to increase those parametric variables. So probably adjust the jet opening, and then also maybe the input flow to create a more robust design space based on 3 variables instead of 1. Also train a 3D model instead of just a 2D model, utilizing one of the DGX A100 machines to train out that model, and convert our macro in SolidWorks to a SolidWorks plugin that has an official user input UI, just to make that user interface a little more slick. And then In addition, we want to directly access the neural network. Right now, the SimNet application itself is doing some of the data handling with the network, and that creates a little bit of a delay. But there are methods within the SimNet framework to use a class to access that network directly, which would require faster results querying. With regards to future applications, what does this kind of tool really offer from an industry standpoint? So one use case we covered today was what you'd call intelligent CAD. Designers interactively understanding the performance of their designs and perhaps using inverse simulation to predict design inputs necessary to get the response that they want. But there are a few other things that you could look at too. Real-time predictive control systems. So, controlling that jet a little more in the real world, with the closed-loop sensing system, and but replacing that sensing system with a closed-loop simulation system. Dynamic prediction of structural deformations, real-time compensation for thermal deformations and stresses. And this is something that's a really hot topic in the metal additive manufacturing space right now. Highly complex geometries, so meshless simulation is especially great for things like porous media. And then digital twins. So SimNet can be used to create a really lightweight real-time simulation that you could then put inside of a larger system simulation in a tool like Omniverse. So really some neat future applications. SimNet is really an amazing technology, and we're really excited to see what the future holds for it.